All right. Another thing that we can do with our understanding of equilibrium constants and equilibrium concentrations and the mass action expression is that when all concentrations but one are known, we can use the mass action expression and C to identify what the missing concentrations are. So here's an example. We have a chemical reaction here. We have a K value associated with it. Now remind me, what does that K mean?
I got an idea. How about you remind me?
Okay, sure. That K value is the mass action expression at equilibrium. It's called the equilibrium constant. Does that help?
Not much, but let me see if I understood. So that down there is the mass action expression.
Oh, right. It's written right here. That's the mass action expression.
And that we got by taking the products raised to their coefficient over the reactants raised to their coefficients. And if we knew all the concentrations at equilibrium, then that resulting quotient value would be K.
That's right. Very good. So, in this chemical reaction, we're told that the resulting concentrations arranged in this configuration equals, when it's reached equilibrium, 4.8 times 10 to the minus 31. And if we're told that the concentrations of N2 and NO are both 2 molar at equilibrium, we can find out what the concentration of oxygen gas is at this equilibrium as well. And this is simply done by taking the 4.8 times 10 to the minus 31, putting in our values that we know here, and then solving for that oxygen value. Got it?
Yeah, okay, got it.
So here's an exercise that you can work on. You guys push pause, try to read through it and figure out what's going on, and then we'll talk about it.
Okay.
All right, hopefully you took time to solve the problem. You should do it. You really should. This is your opportunity to exercise, everyone. So here's the reaction. Here's the concentration of A and B and C at equilibrium. And now we're just going to find what the equilibrium constant is for this temperature. So, how do we do this?
Well, the equilibrium expression is C cubed over A squared times B.
Very good. The concentration of C cubed, right?
Oh, yeah, right.
So the concentration of C is what?
3.
So 3 cubed over what?
2 squared times 1.
All right, so what's 3 cubed?
Is that 9?
3 cubed, 3 squared is 9.
Oh, 3 cubed is 27.
Very good. 27 divided by?
2 squared is 4. 27 divided by 4.
Is 27 divided by 4 6.75?
That's what I got.
Okay, very good. So, again, the equilibrium expression, right? The equilibrium concentrations placed into that expression give us the equilibrium constant, the K value. What the resulting expression's K or value will be once equilibrium is reached. Now, we also have the ability to identify what the equilibrium concentrations will be if we have a chemical reaction, we put in some reactants, and we allow the reaction to come to equilibrium. Now, this is some fun stuff, interesting math, but it's really powerful when we realize what we can do here. So we're going to be using what's called an icebox, and we'll just get right into it. Here's an example of the reaction. Here's the K value. And we want to know the equilibrium concentrations if we start with 2 molar A, 2 molar B, and 5 molar D. All right? To do this, we use an icebox. What an icebox does, I stands for initial, C stands for the change that's going to occur in terms of concentrations. So I is the initial concentration. So the initial concentration for these different components, right? A, B, and D as provided here. C is the change, all right? Now we can look at this quotient and solve it and identify how the shift is going to occur. So what is the Q value?
I can't remember what Q value is.
Well, it's just the quotient, right? It's not necessarily the K value. This equation, or this conditions 2 molar, 2 molar, and 5 molar might be at equilibrium, but it's probably not, right? But we can find out by putting those values in and finding out what the current quotient is. So if I put 5 in, square it, right? That's D, divided by 2 times 2 is 4. So 100 is our current Q value. Did you see how we did that?
Yeah, you just put 5 in, squared it, divided by 2 times 2, yeah.
All right, so we're currently at 100, but we need to get to what if we're going to reach equilibrium?
I don't know.
K is the equilibrium constant.
Oh, okay, 10,000, yeah. So we got to produce more, let's see, if we want to get Q to be a larger value, it's 100, yeah, 100 right now. So we need more products, so we need to shift to the right.
That's right. So from finding our current quotient and comparing it with what the quotient will be when we reach equilibrium, that's what K is, we can tell how the reaction is going to shift, how the concentrations are going to shift. So initial, and this is the change. So we're going to lose some of our reactant, so we say minus some of our reactant, and we're going to gain some of our product, plus. But the amount of product that we gain is going to be twice as much relative to the amount of A or B that we lose, because that's what the stoichiometry tells us. So the change is minus X for A, minus X for B, and plus 2X for D. And then we identify the equilibrium, ICE, initial, change, and then the equilibrium concentration. This is the initial concentration, changing concentration, equilibrium concentration. And the equilibrium concentration is just the sum. 2 minus the X is going to be the equilibrium concentration of A. 2 minus the X is going to be equilibrium concentration for B. 5 plus 2X is going to be the equilibrium concentration for D. All right? So then we can take this value, 5 plus 2X, because that is what is going to be the equilibrium concentration for D. And we can put it right in here to D. We can take this value, 2 minus X, put it right in here for A, and 2 minus X for here, and put it right in here for B. And so the result is, this was identifying whether or not we're going to get a shift to the right or to the left. And the result is 10,000 will equal 5 plus 2x squared over 2 minus x squared. So again, the 2 minus x here and 2 minus x here came together to form the 2 minus x squared. 5 plus 2x, this is the D in the concentration of D at equilibrium squared. And so we can solve this equation. You can just take the square root of top and bottom and have 5 plus 2x over 2 minus x. Set that equal to 10,000, right? If we want to solve this, we got 20,000 minus 10,000 x equals 5 plus 2x, right? We gather our x's, gather our 5. We get 20,000 minus 5, 19,995 equals, add 10,000 and 2x. So then we're going to divide both of these by 10,000 and 2. All right? So 19,995 divided by 10,002. 19,995 divided by 10,002. All right, so our answer is x equals 2, or 1.91. Let's see, I wonder how they got 1.91. Did I make a mistake here? 10,000. No, I think that's probably an error here. It should probably be 1.99. Okay, so what I've done is I've identified the x which is the shift for A, B, and twice this would be the shift for D. And the question is, what are the equilibrium concentrations? So the equilibrium concentration here is 2 minus 1.99, so it's essentially really, really low. 2 minus 1.99, again, very, very low, 0.01. And then 5 plus 2 times 2, which is 4, so this goes up to 9. So our A and B are the difference between the 2 and the x, and our D is the sum of this and 2 of the x's. Okay? So just to recap, we use this ICE table. You see where we got the initial concentrations?
Yeah, we got those from the problem.
That's right. How did we get these changes?
Let's see. I can't remember.
Well, remember, we looked at what the current quotient was, and we looked at what it's supposed to be at equilibrium, and then we decided the shift has to go to the right. So if the shift is going to go to the right, we have to lose x for A and B and gain 2x, because there's 2, the coefficient there has to be included, 2x for each D.
Okay.
And then how do we get these equilibrium concentration?
You just add the initial and the change together.
Very good. And then how did we get the resulting x value?
Solved it using the k value, set the k value equal to those concentrations in that equilibrium expression.
Very good. Excellent. Good job, Fred.
Well, thank you.